Yes, so welcome to Wolverine, the first edition of Wolverine, and hopefully not the last. And it's going to be an experimental workshop. So you know, we hope it works well and that you enjoy, and it's all very productive. I host the first session, or chair the first session, sorry, which is actually the standard part of the workshop. This is we start off with a keynote given by Sheila McIlrath, and we're very happy to host you. So Sheila is, as you can see, she has multiple affiliations: University of Toronto, Vector Institution of Artificial Intelligence, and the Reisman Institute for Technology and Society. Sorry for that. She's a leading figure in the AI community. She is a member. She's a fellow of the ACM and of AAAI. She was PC chair for AAAI and for other leading conferences in this field, and many journals and so forth. And we're very happy to host her. She has done a lot of interesting work on planning and synthesis and LTL synthesis and reinforcement learning and the combination of all of these. To me, this is very interesting to see how these topics are studied from the AI side of things, I mean, coming from the formal method side. So I'm very much looking forward to your talk, and thanks again for joining. Yeah, the floor is yours.
Very good. Well, thank you very much. And thanks for the nice introduction. I'm really happy to be here and to promote synergies between our two communities, because I think there's a lot of interesting overlap, both in what I'm going to talk about today, but in other areas related to formal methods and knowledge representation and automated reasoning. So what I wanted to talk about today, the title of my talk is Formal Languages and Automata for Reward Function Specification and Efficient Reinforcement Learning. And oops, before I begin, I wanted to acknowledge my PhD student, Rodrigo Toro-Carta. Much of what I'm talking about today is his work, or a work that he has led as part of his PhD thesis in collaboration with Torin Klassen and Rick Valenzano, who were, Torin's now a postdoc with me and Rick was a postdoc with me. Torin was my graduate student as well. And some of the work is with Alberto Camacho, who's done a lot of work on LTL and FON synthesis. And some of the things at the periphery are also works that have been done with other students, and I'll mention them towards the end of this work, but kudos to all of them. They're all great students. So the problem that we were the sort of broad problem that we were interested in and continue to be interested in addressing is, how do we advise, instruct, task, and impart knowledge to our AI? And how do they use that knowledge in order to learn? So we're interested in building agents, AI agents that learn and that act in the world. And so I wanted to just pause for a minute and take a little bit of a digression on both sequential decision-making and reinforcement learning, so we're all sort of on the same page. So I know many of you are probably very familiar with sequential decision-making. How do we build a system that decides how to act? And typically what informs that building that system is some sort of representation or model of the environment behavior, a representation of state, which may be partially or fully observable and therefore might be a belief state, the actions of the agent, the effects of those actions on the environment, and also some notion of an objective or reward that the agent is trying to either satisfy or optimize. In the machine learning setting, in a setting where we're a data intensive setting, many of those elements that we might normally model using some sort of a formal language, perhaps LTL or an automata, and do synthesis, or in the AI planning community, using a language like PDDL and some sort of search algorithms or satisfiability algorithms. In reinforcement learning, we don't have all of these elements at our disposal. In particular, we have no model of the environment, and we have no notion of the effects of the actions of the agent on the environment, even though the agent acts, but we have to observe what those effects are. And sometimes, and often it's the case, that we actually don't know the objective of the agent. And so that paradigm is a reinforcement learning paradigm, where the agent, the purple box on the left, performs an action in the environment, And the environment returns the state or the partially observable state of the world together with some sort of a reward. And this trial and error goes around and around with the objective of the agent developing a policy, a mapping from states to action that maximizes its expected cumulative reward. So that's the setting in which we're interested in exploring sequential decision-making in this talk today. And there are two different common approaches. One is where we build a model and then use it, which is called model-based reinforcement learning, and the other is model-free. And we're going to look at the model-free setting today. And in particular, we're going to develop this policy, a mapping from state to an action in a deterministic case or a distribution over actions. And we're going to focus particularly on how we specify the objectives of the agents. And I'll motivate that a little bit further in a minute. The other thing I wanted to mention to you, just to help with us all having the same background, is that a popular way of doing model-free reinforcement learning is via something called Q learning. And a Q is a function of a state and an action that measures the value or the quality of that state. And through interactions with the environment where we're learning, the agent is performing actions and getting states and rewards, we eventually, over time, learn a Q function. And that Q function is updated with each experience, each interaction with the environment. And so the new Q value as a result of some experience is the old Q value plus some weighted notion of any new information that we've achieved from the new experience. So alpha is our learning rate, how much we want to, budge our Q value based upon what our experience that we just had. And that's comprised of the reward that we just got from that experience, plus some discounted future return that we may get. And so there are dynamic programming algorithms and various other techniques for doing this form of Q learning. And that's the approach that we're going to talk about in contrast to in this work. So now that we've had a little bit of a background, I'm going to return to the question that I asked before, which is how do we advise, instruct, task, and impart knowledge to our reinforcement learning agent? And interestingly, the major way that we have to do that is through the reward function. Remember, when an agent performs an action in the world, the environment returns some sort of a reward. And that reward is specified within the environment as a reward function, which is either a mapping, from states to some real number, or a mapping of a state, action, state, triple, successor state, triple, to some sort of a reward. And what actually happens in practice, and when I first started in reinforcement learning, I thought, this is like a dirty little secret. Unlike in the real world, if you think about you and I learning by trial and error, of course, we experience pleasure when we eat a chocolate ice cream cone, or we experience pain when we stub our toe. Any sort of a reinforcement learning agent, even a robot that is deployed in the real world as opposed to through a simulated environment, does not have any sense of reward, what reward it gets from the environment. And so some, usually poor graduate student, has to write this function to reward complex behavior. And it's very, very difficult. And so that is these reward functions are the thing that we're looking at, and that we're using formal languages to help specify and to assist in learning. And in particular, there are a number of challenges to using reinforcement learning in practice. And there's some very good papers that talk about the challenges of using reinforcement learning in practice. But two fundamental challenges are reward specification, that it's really hard to define reward functions for complex tasks. And the second challenge is sample efficiency. It can take billions and billions of interactions with the environment to learn a good policy. You just need to imagine closing your eyes and being plopped in a room where you can press 5 buttons and try to figure out how to, get out of the room and navigate, to understand that we need billions and billions of interactions to build enough understanding of the world to know how to interact, especially when rewards are sparse, especially when many of the things that an agent does do not engender any reward at all. So let me motivate that a little bit more, or ground it a little bit more in this example. So imagine that in some not too distant future, you're able to buy a robot and bring it into your home. I guess we have Roombas that we can bring into our home right now, but imagine it's a robot with a set of skills. Even a robot that already has a set of skills, you're still going to want to task it. You're still going to want to tell it what you want it to do and how you want it to do it. And you need only think about, hiring somebody to come into your home to maybe help with your children, or to help do dishes, or to help around the house, and think of the type of things that you might want to tell that person or that robot. And particular, here are a few just simple examples. Run the dishwasher when it's full or when dishes are needed for the next meal. Make sure the bath temperature is between 38 and 43 degrees Celsius immediately before letting someone enter the bathtub. That's good for a medical robot or a care robot for either a senior or a child. And safety constraints or safety sanity constraints. Do not vacuum while someone in the house is sleeping. You can imagine these rich, temporally extended goals and preferences, so they're non-Markovian. Often they're conflicting, and you want to convey those to your agent. So how do we do that? And it should be no surprise to this community that the one way that we might do that is via linear temporal logic. And I'm assuming this needs no introduction to this community, but of course, linear temporal logic is a compelling logic to express temporal properties of traces. And we have a very simple syntax that is the logical connectives of propositional logic, together with a set of basic temporal modalities, including next, weak next, until, and other LTL operators like eventually, always, and release. And those, of course, allow us to express properties of either infinite or finite traces. And so that linear temporal logic formula can be interpreted over an infinite trace or a finite trace. And of course, as we know, probably this community knows all too well, linear temporal logic can be transformed into automata, into Buchi automata, or into deterministic, non-deterministic, or alternating automata. And that's an important theme that you should remember. We've used linear temporal logic a lot for reinforcement learning, and we've returned to it in some recent work that I'm going to mention at the end of this talk. But the focus of this talk is going to be on automata. But before I do that, just a simple example: do not vacuum while someone is sleeping. You and I would probably write this as a box, but for legibility, always, not, vacuum, and sleeping. We're writing formulae based on a set of simple propositional vocabulary. Vacuum and sleeping are two such elements of those atomic formulae, and we're combining it together using the always modality. And you can imagine more complex ways of representing some of the examples that I used previously. So how do we communicate this to our reinforcement learning agent? We go and look to Noam Chomsky, not for his politics, but for his beautiful work on formal language theory to answer that question. And of course, we use the relationship between LTL and finite state automata and regular languages to specify what we want to specify in the form of automata. And of course, what's typically done is people write Python code. They write reward functions using Python code. That's what your graduate students will do if they're developing reinforcement learning agents. But here we're advocating using automata. And so what I want to talk about in the rest of this talk is something called reward machines, which are automata-like structures that are used to specify reward functions. And I'm going to talk about the following things. I'm going to tell you what reward machines are. I'm going to tell you, importantly, how we actually are able to use that as a normal form representation and exploit reward machine function structure in our learning to really speed up learning. I'm going to show you the results of that in terms of some experiments, and then I'm going to talk to you a little bit about creating reward machines and then recap. My talk is probably around 50 minutes, but if anybody has any questions, feel free to interrupt. I don't know whether there's an easy way to do that, but you can just speak up if you want. I should be able to hear you, so whatever protocol you'd like to use is fine with me. So let's get started. I'm going to describe reward machines in terms of a very simple example. This is a grid world environment that you see on the left, and the task that we're going to talk about is a patrolling task. So in our grid world, we have a little agent who is this purple triangle, and there's furniture, which are these little stars. There's one mail room, 2 coffee stations, and an office. And the task of the agent that I'm going to talk about initially is just a patrolling task. It needs to go from A to B to C to D and back around in perpetuity. So what one would typically do if one wanted to build a reward machine, a reinforcement learning agent that performed this task, is that one would write a reward function for this. And because it's non-Markovian, we have to remember what we did in the past. We might use a counter, an extra variable, in order to describe how to perform that task using in Python. And so the idea of the reward machine is to, instead of using Python, although we could, is to define a reward function using a reward machine, which is basically an automata-like structure using some predefined vocabulary. And what we have typically done, although it need not be the case, is to argue for a vocabulary that is interpretable and that is meaningful to a human being in the case where a human being is actually specifying these reward machines and these reward functions. Now, that need not be the case, that it need not be specified by a human being, but if we think about it in this context, somebody programmed this, instead they're going to write a reward machine in terms of things that the human being knows, which are coffee station, whether you're at the coffee station or not, whether you're at the mailroom or not, whether you're at the office or not, and so on. So the vocabulary can comprise human interpretable events or properties realized via detectors over the environment state, or it can conceivably be learned and be over a set of propositions or noisy propositions that may or may not be human interpretable if the reward function is going to be learned. So a reward machine, again, is comprised of a finite set of states here, U0, U1, U2, U3, which talks about we go to A, and then once we've been to A, we go to B, then C, then D, and then back again. An initial state, U0, a set of labeled transitions where the labels comprise 2 things. The labels comprise a logical condition here, whether A is true or not, whether the agent is A, whether the agent is B, and so on, and also a reward function or constant. And I'll return to that in a minute. Right now, the reward is just a scalar, and it gives a value of 0. So you can see that it's 0 everywhere except when you've gotten through the automata and you've transitioned to D, and then you get a reward of 1. So reward machine, historically, when we described reward machines, we described them as a Mealy machine over the input alphabet, whose output alphabet is a set of Markovian reward functions. But more generally, and this is a definition that's in a paper that is on archive now, but it's been accepted for publication. It's just going into production. A reward machine is basically comprised of a set of propositional symbols, a set of environment states, a set of actions, and the reward machine itself is a tuple that involves those states, the initial state, a final state, and then 2 transition functions. One that maps, that transitions the state of the reward machine based upon the values of those propositions. That's delta U. And then the other reward function is a state reward function that maps your position in the reward machine, what state you're in the reward machine, to actually a function. So you can have an arbitrary function. What my example here today is a simple reward machine where that reward function, that mapping, it just goes to a scalar value. That's a simple reward machine. But again, we can have an arbitrary function as well. So let's just see our reward machine in action very quickly. Hopefully everybody's gotten that, but I've got my little agent down here in the bottom. It's just entered our grid world, and it's at U0, and it moves around and it stays at U0, and it circles at U0 until it gets a reward of 0 until it gets to A, at which point it transitions. It tells the reward machine that it's at A, and the reward machine transitions it from U0 to U1. But as we can see, it's going to get a reward of 0 rather. And it moves around, staying at U1, 1, 2, skip a few, goes to B, transitions to U2. I'm not going to go all the way along, but the interesting thing, of course, is that when it finally goes to D, it gets a reward of 1, and then it cycles again. So we can define all sorts of different reward machines. Not surprisingly, deliver the coffee to the office while avoiding furniture. We get the coffee and then we go to the office. As long as no furniture has been hit, we transition to U3 and get a reward of 1. But if we hit if we hit any furniture, this is like a safety condition, we go into this sync state, this U2 state, where we stay in perpetuity and can never get the reward of 1 because we have violated the safety constraint of our specification. Similarly, deliver coffee and mail. Of course, we can deliver the coffee and then the mail, the coffee, then the mail, and then go to the office and get a reward of 1. Or we can do the mail first and then the coffee and then get a reward of 1. So we can have partially ordered tasks as well, and all of the richness that I'm sure you all know of propositional logic and linear temporal logic combined together, and the expressiveness of a regular language, basically, which is what we have with our finite state automata. So now that you've seen what a reward machine is, that's this representation of the reward function, let's see how we're going to exploit it in learning. And this is actually the another interesting aspect of this work. So it's based on a very simple idea. And it's funny, I think often when one comes from a different community, one sees ideas that other people don't necessarily see. And this is a simple one indeed, which is that someone always has to program the reward function, even when the environment is the real world. And of course, this goes back to my comment about the ice cream, that these agents that we're building are not wired to feel or to have inherent reward from domain specific things. It has to be programmed. There can be domain independent reward, curiosity or various other things, but this notion of garnering reward from the environment has to be programmed. And so the simple idea, and when that is done, the reward function is actually treated as a black box. You move, the agent operates in the environment just tells it what reward it gets, a 0 or a 1. Depending upon a 0, a 1, or some other number, depending upon what it's doing. But so the simple idea is to give agent access to the reward function and to exploit that reward function structure in its learning. So rather than having a black box, we're going to have a glass box. But we're not going to share the Python code. What we're going to share is the automata. And we're going to exploit that automata in learning. And I'm going to tell you how we do that. And I'm going to tell you in the context of several different techniques that we developed for exploiting reward machine structure. So the first 3 that I'm going to mention, I call them baselines because they're not as good as the techniques that we developed, but they're not really baselines because they are of our own creation, but they didn't, in the general case, they didn't perform as well as this new algorithm that we developed. So I'm going to tell you about 5 different methods in succession, and I'm going to illustrate, and then I'm going to show you how well they did. So the first is basically to use Q-learning, which we talked about at the beginning. But we want to observe one thing, and we want to augment our Q-learning baseline. So a reward machine may define a non-Markovian reward function. And I guess that's probably obvious to you from our discussion of linear temporal logic at the beginning, but just to really ground it, let me just illustrate, which is the following. If my little agent is here adjacent to D, then the reward that it gets depends on the history. It is non-Markovian. So for example, if that agent just came from A and went directly to its position and then to D, it would have been in U1. And so when it moved to D from U1, it would have gotten a reward of 0. That same agent in the same position, if it had gone from A to B to C to D, and then moved into the D position, it would have been at U3 moving into the D position, and therefore it would have gotten a reward of 1. So again, depending upon the past history, the reward is going to be different. So we have a non-Markovian reward that is captured made Markovian by the information that's in our reward function. And so an obvious thing to do is just to include the reward machine state as part of the agent state representation, and then to use standard Q-learning on the resulting MDP. And that was our first baseline. That was a simple thing that we did, just as to show that there was, we were using the reward machine in some meaningful way. But we did much better than that. And let me tell you a couple of different things that we did. So the second thing we wanted to do was to use something called option-based hierarchical reinforcement learning. And some of you may know what that is, and some of you may not, but there's, for 20 or 30 years, there's been some work on hierarchical reinforcement learning, which develops something called an option, which is a temporal abstraction or a macro action, if you want to think of it that way. And there are option policies that can be learned. And so we wanted to try to use hierarchical reinforcement learning with our reward machine. So learn one, and the idea was to learn one option policy, one sort of macro action, if you want to think about it, for every different, for each proposition mentioned in the reward machine. And so the reward machine refers to A, B, C, and D. And so we would learn a policy, pi of A, pi of B, pi of C, and pi of D. We'd optimize each of those policies to satisfy I optimally, the thing that we were trying to achieve. And then we would use hierarchical reinforcement learning, a meta controller, which is what's typically done in hierarchical reinforcement learning. As depicted here. The meta controller would take those options and figure out what to do in a particular circumstance, which is how hierarchical reinforcement learning works. And hierarchical reinforcement learning is a very effective technique. The third thing we decided to do was hierarchical reinforcement learning using our reward machine structure. So we have this structure. So if we're monitoring the structure of our reward machine, why not let the meta controller have access to it and prune any policies that are irrelevant given the context we're in? And so we augmented the meta controller with that pruning function so that if we were at U0, we wouldn't contemplate using the policy that you were meant to use at B or the policy that you were meant to use at C. Rather, we would use the appropriate policy for the context that we were in. So a context-specific pruning using the reward machine structure. And that was our third baseline. But the problem with hierarchical reinforcement learning methods, or a limitation of them, even though they work very well, is that they are myopic. So hierarchical reinforcement learning methods can find suboptimal policies. And I'm going to illustrate that in terms of this very simple example. So imagine that I want to go, the thing I do every morning when I'm at the university, I want to go and get a cup of coffee, and then I want to go to my office. And so if I were an agent in this particular grid world environment, what hierarchical reinforcement learning does is it always finds locally optimal solutions. So if my agent is here, then the locally optimal, then the globally optimal solution is to go to the far coffee station, which is very close to my office, and then go to my office. So that's a non-myopic solution. But what hierarchical reinforcement learning does is not that globally optimal solution. Rather, it picks policies one by one myopically. And so it decides to go to the closest coffee station because it's myopically optimizing for the best way to get to a coffee station from where it is. And then subsequently, it has to take a very long circuitous route in order to get to my office, which obviously leads to an overall policy that is suboptimal. And that's one of the problems that we have with hierarchical reinforcement learning. And you'll see that manifest in the experiments that I'll show you in a minute. But that observation actually motivated us not to develop a hierarchical, a myopic policy. And so in particular, what I want to talk to you about now is QRM, which is Q learning for reward machines. It's an algorithm that we developed, and we have a newer version of it called CRM that is in that is not much different. That's in the paper that is about the journal paper that is about to be published, and it's available on arXiv. So I'm going to tell you a little bit about QRM and then about reward shaping, and then I'll show you some experiments. So the idea of Q learning with reward machines is the following. We're going to learn one policy or Q value per state in the reward machine. We're going to select actions using the policy of the current reward machine. So if you're in U0, you're going to use Q0. If you're in U1, you're going to use Q1, and so on. And then what we're going to do, and this is the secret sauce, we're going to, again, we're interacting in the environment, learning. We're going to reuse experience to update all the Q values for Q0, Q1, Q2, Q3 via what's referred to as off-policy reinforcement learning. And it's a form of counterfactual reasoning. So even though I may have just entered the grid and I may be at U0 and I do a particular move and I update my Q value for Q0, I'm going to say, if instead of being at U0, if I'd been at U1, what would the effect have been on Q1? Or if I'd been at U2, what would the effect have been at Q2? So just to again, we're going to select it. I'm going to ground this in a very simple example. We're going to select an action according to the current reward machine state. I'm going to update each Q value as if the reward machine were in that corresponding state. And by exploiting that structure, we're going to learn much more quickly than we would have learned had we just had a typical Q learning, reinforcement learning. And so again, if I'm here and I'm in U0, I'll get a reward and I'll update this Q function. So Q0 is going to be updated with the reward I've just got, plus some discounted value of my expected future return, which is that I'm assuming I'm going to be at U0 again, because that's where I am. However, if I'm here at U3, and I get that, if I counterfactually assume that I'm at U3 with the same experience, the same move from that left square into the D position, I can also update Q3 and Q1 and Q2, but I just didn't put the examples in. So Q3 is going to be updated, but it's going to get a reward of 1. And the future return is going to be with respect to Q0, because that action is going to transition me to another state. And so you can see that we've had one experience, but we're updating all these different Q values simultaneously. And this using something called off-policy learning. And this is going to really, really speed up learning. So the final thing that we did after we did this QRM algorithm, and I'm going to show you the results in a minute, was something called reward shaping. And I'm not describing reward shaping in detail here. You can look it up. But just the intuition of reward shaping is to address the problem of sparse rewards. Often when these agents operate in the environment, they only get reward after they've done, after they've done some particular task or sporadically. And what that means is that a lot of the time these reinforcement learning agents are getting zeros. You move somewhere 0, you move somewhere 0, and that's not helping it learn. And so in an effort to help with learning, Andrew Ng and Harada and Stuart Russell developed something called reward shaping, which is just augmenting the reward function with a potential function that actually preserves the optimality guarantees that are associated with Q learning. Actually, I should have said Q learning is guaranteed to converge to the optimal policy in the limit when we're using tabular reinforcement learning, when we're not approximating the state. So reward shaping preserves those optimality guarantees, but you can think of it as taking the cookie that you get at when you finally, or the reward you get when you finally get to the coffee, to your office, and sprinkling that cookie along your path to give you, like Hansel and Gretel, to give you little rewards that will keep you walking in the right direction or sting you when you're going in the wrong direction. And so to look at this example, we're going to treat we're going to augment our reward, as we've done here in red, with extra reward, positive reward, or negative reward. And we're going to do that reward shaping by doing value iteration over the reward machine, which is a very nice principled way of actually doing that reward shaping. There are many ways to do reward shaping, many different algorithms, and you just have to define this potential function. And if you do it appropriately, you're guaranteed to preserve optimality. But this is how we did it with our reward shaping technique. We actually did value iteration over the reward machine and augmented our reward machine in order to give a few more clues. And here, this is a pretty small reward machine, but it really does help in many cases. So just some properties, both QRM and QRM with reward shaping converge to the optimal policy in the limit when we're doing tabular RL. and maybe a more general statement of the theorem, and again, these are informally stated for the purposes of this talk, is that we preserve any optimality guarantees that the original algorithm, the original Q-learning algorithm preserved. So in the case of tabular, we preserve optimality guarantees, but when we move to deep learning and use Q-learning or other techniques with deep learning, we lose those optimality guarantees, just as every other optimality, every other system does. And in contrast to hierarchical reinforcement learning, where there are no optimality guarantees, as I illustrated with that suboptimal, you know, that myopic strategy that HRL, hierarchical reinforcement learning, uses. Okay, so I've told you how to specify functions using reward machines. I've talked to you about how we can use that function structure in order to learn more quickly. And now what I want to do is talk to you about some of the experiments that we ran. So we tested, I'm going to talk here about two domains, an office domain with 4 different tasks, a craft domain, which is like a Minecraft domain with 10 different tasks. These are in discrete actions and state spaces. And then some continuous state space domains that using something called the water world domain. We've also done some other work with the with continuous domains that you can see in our paper, but again, similar results, but I guess just more impressive gated agents that are doing mobility tasks in continuous state space. So like with half cheetah and various other, for those of you who are familiar with those things. So we tested on all 5 of our approaches. I wanted just in this discrete domains, I wanted to note that Q-learning preserves optimality, as do our QRM and QRM with reward machines, but hierarchical reinforcement learning and hierarchical reinforcement learning with reward machines do not have any optimality guarantees. And all of them, except for Q-learning, use some form of decomposition of the structure. And so we can see from our results, again, we're back in this office world domain. We had the patrolling task, but a bunch of other tasks like delivering coffee and going to the office and picking up mail and various other things. And I'm going to show you the results in this table on the right, or this graph on the right. On the x-axis, the horizontal axis, we have the number of training steps, and you can see that goes up to 50,000, which is actually not that much for reinforcement learning. And on the y or vertical axis, we have normalized discounted reward, so that we can compare all of our different results. We've normalized all the results to 1, so that 1 is optimal, and then we can look at our the different results. And so what we see here, QRM is in red, and you can see that with a very short, relatively short number of training steps, it very quickly converges to an optimal policy and stays there. In contrast, at the other end of the spectrum, Q-learning, which was just used, you know, it just was augmented with the automata states, flatlines for quite a long time, and never actually, in the time that we gave after 50,000 training steps, was able to reach the optimal value. But remember, Q-learning is guaranteed to converge to the optimal policy. And so at some point off this slide to the right, there will be a point at which it will get to 1, but it of course needs more and more and more training steps because it's not getting enough signal from the environment and it's not able to exploit that function structure. The other 2 lines that we see here are hierarchical reinforcement learning in yellow, and then the other one in blue, where we were using the reward machine to prune the policies that we knew were not appropriate given the context that our reward machine was capturing. And again, what we're seeing here, because the hierarchical reinforcement learning is myopic, that in some of these cases, it was not able to reach the optimal because it was always choosing a myopic suboptimal solution. We had similar results in a craft world domain, which was like a Minecraft-like domain where we had 10 random tasks over different types of maps. And we were doing, collecting wood and making axes, and we had safety constraints as well in there. And again, what you'll see is the same thing, that our red QRM approach very quickly and converged to an optimal policy. And again, I want to contrast that with with Q learning itself, which is completely flatlined. So Q learning, even after 10 to the 6th experiences, was unable to make any sort of gain towards a policy. And yet again, this blue line in the limit will converge to an optimal policy, but it's just not able to exploit the structure. And again, we see these two different versions of HRL, again, confounded a little bit by the fact that they are unable to always reach the optimal solution. We also did work with, of course, deep learning is so important particularly with perceptual tasks. And when you do deep learning, what you often, well, what you do is you approximate the state. You use function approximation because you just have so much data. And so we replaced Q learning with double DQN, which was the state of the art at the time that we were using this work, and prioritized experience replay. We've since done more work, and I'll show you a little bit at the very end. But again, because we're using function approximation, our convergence guarantees, as are everybody else's, are at the roof. But again, we got very good results. This particular domain was something called the water world domain. It's like a bunch of bouncing billiard balls, and the agent is the little white cue ball. And the tasks that we asked the agent to perform were, never touch a yellow ball or hit 2 green balls and then a pink ball, temporally extended types of tasks. And again, which was very impressive at the time we did this work, was that double DQN augmented with a modified version of our QRM algorithm achieved much better performance than both hierarchical reinforcement learning techniques and also Q learning, which is again down at the bottom. So this was very nice results. What I want to talk to you about, and that's all I'm going to tell you about reward machines and learning with reward machines here, but I want to tell you a little bit more about the bigger picture of this work. So, and some other work that we've done. So creating reward machines. So here you might assume that we created the reward machine by specifying that finite state automaton. But of course, there are many different ways of creating reward machines. We can specify them, we can generate them, and we can learn them. And we've done work on all of these different ways of generating reward machines. And so just very quickly as an advertisement for those who may want to look at it later, it probably comes as no surprise to this community that, one size does not fit all. One language is not always the best language for specifying reward. And certainly I've done a lot of work over the past 15 years specifying goals and preferences for planning with models. And we've used all sorts of regular languages, some with while loops and if then else, some using LTL over finite traces, LTL over infinite traces. One size does not fit all. And so what the message that I guess I wanted to convey was that you can specify in any formal language that is translatable to finite state automata and then still benefit from reward machines. So dialects of LTL, GoLog, LTL, linear dynamic logic, past LTL, regular language, again, the variants that are translatable into finite state, into DFAs. And the reward machines can serve as a lingua franca to provide a normal form representation for these reward functions that support reward function tailored learning, that are able to exploit that structure that is exposed by the automata. And so the idea is simply to, translate to a DFA and then to a reward machine, and then use any sort of algorithm that you want. And the beauty is that if we're going to use all these different languages and we want to exploit structure, then we're going to have to write learning methods for each of those languages. But here, by using the automata as sort of a lingua franca or as a normal form, we're able to translate into those automata and then use reward the algorithms that already exist. And that's a really nice feature of this work, even though we do actually have techniques for LTL specifically as well. The second thing I wanted to mention is that in addition to sort of specifying reward machines, we can also generate reward machines using a symbolic planner. And the idea is the following. We can, one thinks about wanting to really task an agent, to have a robot in your home that you can say, hey, get my glasses for me, and not figure out, you know, all the gory details. And yet we know that by providing more instructions, by providing more information, there's less sparse reward, and the agents will learn how to do tasks more quickly. And so the idea that we wanted to explore was to use a high level, a set of abstract actions, a set of abstract and final state goals, and use a symbolic planner to generate instructions, to generate a sort of filled out set sequence of actions to achieve a final state goal. We deordered those actions based upon into partial order, into partial order representation that then represented many different possible realizations. And then we used that high level specification using reward machines and hierarchical reinforcement learning to actually generate solutions more quickly. And so we were able to generate these reward machines using a symbolic planner and simple high level actions. And I'm not going to talk about it anymore today, but it's very interesting work and something you might be interested in. Again, code is available for all of these things. So the third thing that I wanted to mention, and I think this is really interesting work, and I don't have time to mention it here, but I wanted to just give a little shout out to it, is that in addition to the two challenges related to reinforcement learning that I mentioned, which is really hard to specify reward functions, and also that this notion of sparse reward, and that it takes the sample complexity takes so many experiences. The other problem with real world reinforcement learning is that the world is inherently partially observable. You know, maybe for the types of problems that we can solve where we can generate models, maybe we have a fully observable environment, but often if we have sensors, we don't have enough information to make an environment fully observable. And so it's inherently partially observable. And so what we wanted to look at here was how we would learn reinforcement reward machines in partially observable environments. And we constructed this very simple example. There are a couple of them that are the same, and I'm going to describe it to you because it's sort of a cute example, and I think it brings home this idea. So imagine you see this image on the left, and you're a little agent. And this is the way that the environment works for those of us who know. The agent doesn't know this. You have to go up to this yellow room and press this button. And when you press a button, a cookie magically appears in either the blue room or the red room. And then what you want to go do is eat the cookie. The agent wants to eat the cookie. You want the agent to eat the cookie, and the agent's, at which point it gets some reward. So the agent's goal in life, as should be all of ours, is to eat as many cookies as possible and to maximize its expected cumulative reward. But the problem is the following: the agent doesn't know anything about the environment and it can only see in the room that it's in. So it doesn't have this bird's eye view that we have on the left where it can see the full state, see where the cookie is. For example, it only sees these black boxes. And yet, when it comes to this junction, this T junction, what it does next depends on what it did in the past. But we're not going to specify the reward function. We want it to learn this reward function. We want it to learn sufficient memory to figure out what it needs to learn in order to act. So if it's just eaten a cookie, then it needs to know that it goes up and to press a button. If it's pressed the button, but it hasn't eaten a cookie, then it needs to go to one of the rooms. And if it finds a cookie and eats the cookie, then it's back here having just eaten a cookie. But if it doesn't, then it needs to know that it needs to go to the other room. So we want the reward machine to learn this external state memory. And we actually did this. These are, this looks like a really simple problem, by the way, but these toy problems cannot be solved by the state of the art. And we learned these reward machines using discrete optimization via taboo search. And we were able to learn reward machines like this, given a vocabulary of, what room you're in, whether you've eaten a cookie, and whether you've pressed a button or not, in order to learn a reward machine of this sort. And I won't go into the explanation for this reward machine. If you're quick, you can trace through it and figure out what it does, but it does exactly what you would think it should do. And as I described it, and we were able to learn these reward machines, and this was published at NeurIPS in 2019. And by doing this, and then by learning reward machines, LRM, and combining it with our deep Q learning for reward machines, DQN, either actually learning it with our QRM algorithm, or even with just double DQN, we were able to really do well on these hard problems, whereas all these state-of-the-art deep learning systems for reinforcement learning were just flatlining. So A3C, ACER, all these different techniques were really flatlining, whereas we were able to get really good performance. So I'm done with time left for questions. I'm just going to recap again, just for those of you who hopefully didn't fall asleep, but maybe went to get a coffee. The problem, the general problem that we're interested in is how do we advise, instruct, task, and impart knowledge to our AI that learns. And the big idea was to develop this notion of reward machines, which was both to represent our Python functions as automata and to exploit that automata structure in learning. So to reveal the reward function to the agent so that it could exploit that structure in learning. And we got great results in discrete rote domains and in continuous domains by doing that. We can construct reward machines for a diversity of different formal languages. We can generate them using symbolic planning, and we can learn them. We can to solve hard problems in partially observable environments, and these really are hard problems. And we've got lots of papers and code. The best ambassador to this work, Rodrigo Toro-Accardo, who's my student, who I'll just show you his picture again, has, if you go to his webpage or his Bitbucket, he has all of the code for both QRM and for CRM, which is, we've got work on not only on the reward machines, but on LTL, if you're interested in LTL. We can translate from LTL to reward machines. We've done some, and so there are a bunch of different papers, anyways, they're listed here. We've got some more recent work on, again, this paper that's coming out that's on arXiv, but also some very interesting work on generalizing LTL instructions for multitask reinforcement learning that appeared at ICML this past year, where we're actually, reinforcement learning agents are actually learning the language of LTL and how to follow it to generalize instructions to a bunch of different domains that they haven't seen before, which is actually quite interesting. We've got some other related work on advice and on learning LTL, learning interpretable LTL that Alberto Camacho did. We have a transmographer, a translator that is sort of in alpha or beta mode, but it does do some translation. And then we've done a lot of, for those of you who are just interested in sequential decision making, over the past, I'd say 15 years, we've done a lot of work on planning with LTL. And with lifted LTL on finite and infinite traces. We've done heuristic search techniques, and those might be of interest to people. And then more recently, some work with fully observable non-deterministic planning that my other PhD student, Alberto Camacho, did that relates to LTL synthesis. And that might be something that people are interested in. So again, acknowledgements to Rodrigo Toro-Accardo for this body of work, together with his collaborators, me, but also Torin Klassen and Rick Villanzano, some of it with Alberto, a small amount of it with Alberto Camacho, and some of it with all of these other great students in my lab. So I think that's it. So I'm going to stop sharing and say thank you very much. And I think we have just a few minutes for questions if anybody has any. So thank you.
Hey, thanks for the very nice talk. There is already one question on the chat. So if Manuel is around, you can ask in person.
Yes, I am here. Yeah, I was listening, very nice talk, and I come more from the formal synthesis world. So I was trying to make some parallelisms to how I will approach this whole problem. And to me, my starting point was, well, a Q function seems like what in control we will call a control Lyapunov function. So it's something that tells you if you maximize the gradient from this point, you're gonna get to where you want to get to, right? And in a sense, it sounds like these reward machines are trying to build, are basically a way of specifying that Q function indirectly. Right, by integrating over time steps of this machine, eventually, you know, like if you do back propagation, you get your Q function. Am I on the right path?
Yeah. So one way to think about the reward machine is a sort of a non-Markovian decomposition. So what's embodied in there is, at least at this abstract level, some notion of a transition function. I mean, again, the premise is that you don't, unlike when we do synthesis or with a model where we have the transition function and we can manipulate it as part of our reasoning, we only have experience. So when I press a button, I don't know what happens. It could take me to Paris, France, or it could, move me one step forward in the grid. I don't know what the outcome is going to be. So over time, I need sufficient experiences to update and understand the transitions. But yeah, you're absolutely right in the sense, I think that if I'm understanding you correctly, the reward machine itself is embodying both it's like a Markovian decomposition of the reward function. So it's focused on but that captures sufficient dynamics to predict the reward. And so
sorry, it's very embarrassing, but I locked out my family out of my house. So
okay.
I'll be back in a second.
Yeah, no problem.
Maybe we can ask a different question to them.
Yes, any other questions in the meantime?
I'm back. That was just 1 second. Yeah, so what I wanted to get to is that what it looked like to me when you were solving this QRM, it looked like you're taking your map and your dynamics, which I presume that you know, so where you land with each of the actions.
No, we don't know that.
Oh, that's not known. So that's what will be you're learning actually the dynamics of the environment.
Yeah. So the only you perform an action, and it tells you what the state is. You do not. That's the challenge. You do not know the dynamics of the environment. But to your point, which I think was an important one, is that some aspects of the dynamics relevant to the reward function, this non-Markovian reward function, are embodied in the reward machine. So the reward machine can be thought of as a Markovian decomposition of this non-Markovian reward. And we are sharing that reward machine with the agent, which is one of the things that we did. Like normally it's treated as a black box. You just do something and you get, 1, 100, minus 50, you just perform an action and you have to figure out what to do. It really is a different, it's very different from synthesis in that regard, because you do not have the transition function. But here, what we do have is the dynamics of the reward machine, which helps a little bit.
But this allows you anyways to basically do somehow like you could do a formal synthesis over the actions of this reward machine. And then what you do is learn quotient anything that is not safe.
Yeah.
Is it that the spirit of what you're doing? Because that's kind of like how it almost sounded to me in your description. Like you kind of want to get rid of all the actions that will not get you in the shortest way on your reward machine to the reward.
That's right, but there can be many, many thousands of actions before you get a signal that transitions you in the reward machine. So imagine it's a difference between, I can tell you, I might write up, when we do planning, I may say, pick up the cup, and the action is pick up in some abstract space. But imagine all of the control information involved in this end effector in order to move it into the right location, to grasp it without destroying the mug, but to hold it strong enough to be able to hold it and then lift it. And so all of those actions, that large number of actions, need to be learned in order to this abstract level, get to the point where the cup is picked up. And so it's quite complex. And again, in those and those are the interesting environments. And we did this work with, there are these challenge problems. There's a half cheetah where you're trying to control an agent that is a mobile agent, and there's some high level signal, but most of the time it's sparse, which is why we use these sort of reward shaping techniques as well. But there's a myriad of things you can use it. You can use it some closer to what you were thinking about, but also but it's not that trivial not that straightforward. I shouldn't say trivial, not that straightforward in the general case. Yeah.
Thank you.
Yeah.
So there is another question. Abhinav, if you want to ask him personal. Thank you.
Yeah, thanks. Thanks for the great talk. I was hoping if you could give us a bit more information of applying this technique to continuous state and action domains. Particularly, it seems that with this kind of construction, if your action domain is continuous, it would be hard to sort of translate it into the Q-learning framework, which requires finite Q table to be created. So are there any particular challenges there which you've already addressed?
Yes. So in the continuous domains, and I glossed over it very quickly. So we do it with deep learning. So but I have a better, more nuanced answer to your question. So we do it with deep learning. So even the experiments in 2018, we used double DQN and various other function approximation methods. And so there's a very, same sort of, in the same way that there's deep Q learning, we did double DQN, and we created a version of QRM for reward machines that uses deep learning. So it's not tabular. But what is the case, which I think is, and we've got, again, more experience now with Cheetah that are using these continuous control, complex continuous control domains that you can see on arXiv, and they're in production. The paper will be published in JAIR soon. But what we don't do, I would say a limitation of what we've done right now is that we assume that we have these, at least for this work, for that particular work, we assume that our event detectors are propositional, that they're either true or false, as opposed to noisy. And so I would say that one interesting thing, and it's something that we've looked at a little bit, and I think maybe some other people have started looking at, because other people are picking up reward machines as well, is this notion that whether you're at the office or not may or may not be something that you can answer as a 0-1, that there may be noise associated with that. And so even where you are within the reward machine may require some sort of belief state estimation as well. And I think that that's an interesting area to move forward, not so much for the types of problems I was describing, but certainly there are classes of problems where if you have noisy sensors and you don't have this propositional language where you might want to do it. The other thing that's interesting, of course, and that's already, when I describe this, all of the language of the reward machine is interpretable. We can all see, oh yeah, A, B, C, or coffee. But of course, when you think about deep learning with perceptual tasks, what people are now doing is that they take this, their pixels, and they map into some latent space where which has a set of features or some sort of basis set that is not necessarily interpretable or meaningful to us. And out of that, one would engender a reward machine or something else. And so again, the fidelity of knowing what state you're in the reward machine is going to be important. So I hope that answers your question.
Absolutely. Thank you.
Yeah.
So thanks again. I think we should close this session again. Round of applause.